Okay, my screen is visible, right? Can anyone give that?
Yes, sir.
Thank you. Okay, so yesterday we were almost finishing the OpenGL lecture, but I think the last part it was a bit hurried, so I'll quickly wrap these things up and tell a bit about the transformation, and then we switch to the next topic. Okay. So you remember that yesterday I was discussing about this push matrix and pop matrix. So they are usually used to manipulate transformations in OpenGL. So mostly the order of transformation and how the object. I mean, let's say if you're using like one set of transformation and what will happen in the next transformation. So will that affect the previous one also? All these things are handled by push matrix and pop matrix. So this in this example, what I was trying to show is that uh, by using a series of push matrix and pop matrix, you can customize your transformation parameters or transformation sequence. So let's say initially we do a push matrix. Okay, so that means it creates a matrix in a stack. So this is a stack, and let's say this is M1, this is matrix 1. So now let's say I'm translating the object by amount 5 along x-axis. So that means GL translated 500. So that means it's simple. So you have matrix M1 and you apply transformation to M1. So there is nothing complicated about this. Now, if you draw a square, so let's say this is your function for drawing a square. So it will draw a square with transformation 500. Okay. So that means that square won't be drawn at the origin if origin was the starting point. So it will be drawn somewhere here at 5 at x-axis. Okay. So now let's say if you do push matrix again. So then what happens? It creates another matrix basically, duplicates matrix 1 on top of matrix on top of matrix 1, and let's call it matrix 2. Okay. And then if you do scaling, so it won't actually affect the matrix M1. So it will deal only with the matrix M2. So that means scales matrix M2 only by 5 amount. Okay. So now if you draw a square at this current moment, what happens? Previously scaling was done on matrix 2, but the stack contains both matrix M1 and M2. So that means the square will be drawn both with uh, transformation and with pop matrix. Why? Because it was already translated. So it was already translated by of 5 amount. So now let's say I'm doing a pop matrix. So that means I'm removing the top one. So that means M2 will be removed and M1 remains. So now if you draw the square, so there is no scaling effect because I have already removed it, right? So it's like to draw the square only with transformation 500. And eventually if I pop the matrix and nothing is there, then we are basically done. So this is how actually this push matrix and pop matrix usually works. And whenever you do these transformation functions, so you have to use this push matrix and pop matrix because everything in OpenGL works as a stack in this case of transformation functions. Okay, so I will show you an example of transformation in OpenGL. Make sure that you understand this correctly. Okay. So I was showing an example here, but let me see. Okay, maybe I will explain here. That's much better. Okay. Okay. Just a minute. Okay. So the thing is that the most important thing is that in OpenGL, translation and rotation are order dependent. Okay. So translation and rotation are order dependent. That means if we apply translation first and then rotation second, and you do the vice versa, then they are not the same. Let's take an example. Let's say that we have one object like this. Let's say this is your, let's consider 2D, okay? So is there a problem here? No, okay. So okay, let's do one thing. First do the translation, then the rotation, and then rotation followed by translation, and then see what happens. Okay. So first we will do translation. Okay. So let's call it GL translate f. Well, let's say -1 0 0. Okay. And then we do GL rotate f, and we do rotation by 60 degrees along. Okay, okay. This one I should not say about like this. So maybe this 0 should not be there. 0 1 it should be anywhere. Okay, but whatever. And then in the second case we do the opposite. Okay, so GL rotate F. Okay, actually we can keep it here. 0 0 1. Let's consider that it's in a like a dimension case or whatever. Okay, and then GL translative and the same -1 0 0. Okay. So in this case, what happens after you translate this? This is pretty simple. Basically, it translates by -1 amount along the. Let's draw the coordinate axis and then we'll see what happens. So if you translate this by -1, so that means it will come here. Okay, and then if you rotate it by 60 degrees, so this is again it's a very simple thing. So basically, it will look something like this. Okay, but now if you do the rotation first, so that means in this case you rotate this by 60 degrees, so that means this one is simple, that means it looks like this. But the problem is that the way OpenGL actually behaves is it depends on the local coordinate system. So we are assuming that these are all like a global coordinate system, but whenever you do something with the rotation, it actually affects the local coordinate system. So that means as if there is a kind of coordinate system associated with this, like this one, you can assume something like this. So then what happens if you again try to translate this? So translate around the x-axis. So now what is the x-axis? So this is the x-axis now because this is already rotated. So that means it will be rotated from translated from here along the negative x-axis. So that means it will be coming from here to here. So you see that these two results are not the same. So that means rotation and translations are order dependent in OpenGL. So this happens because of this feature of OpenGL, where actually it's heavily relies on the local coordinate system. Okay, so actually composing, let's say, what is the like notational aspect of
Sir,
this?
one question.
Yes, yes, yes.
Sir, this rotation or translation,
Mhm.
from which part, if the object is big enough, from which part that means that value is calculated, whether
So
it
I
is from
mean,
the center or for
yes,
the
you can consider it from
coordinates?
the center. Yes, yes, you can consider it from the center. Or it, even like rotation is like if you consider rotation from the center, then it's correct. But translation is the same, right? I mean, if you translate this part and this part, this is a rigid object. So I mean, if this is your object, you move it by 5 amount and you also move it by 5 amount, the shape remains the same, right? There is no change.
Yes.
But for the rotation, I mean, you can consider it like along the center. So basically rotate it like this. It depends on your application. So now here, I mean, I'm just showing about the rotation among center. But you can consider other parts also, no problem. But as long as it's a rigid object, there is no problem. Okay?
Okay,
Is it
sir.
okay?
Thank you.
Okay.
Sir,
Yes.
sir, what is the axis of rotation in the
I
first
cannot
case?
hear you. Can you please speak a bit louder?
Sir, what is the axis of rotation in the first case?
So in the first case, I'm rotating about this y-axis. Sorry, this is, yes, I'm rotating about the y-axis. Yes, in both cases actually.
Z axis or y?
Sorry, it's very low. Your voice is very low. Can you please turn on
Sir,
your
is it z axis or y axis?
z-axis or y? Oh, actually here I'm not showing the 3D. So that's why, although I'm writing here, it's a 3D, but you can assume that it's along y-axis. I mean, if I show in 3D here, things looks a bit complicated or messy. So that's why, but you can assume it's like a y-axis. Okay. Is it okay with you? Can you hear me?
Hello, sir.
Yes.
Okay.
Is it okay with you? Is your voice is extremely low? I cannot hear anything. Is it okay? Okay, maybe we move on. So here, so you can specify the rotation axis. So you can read about x-axis, y-axis, or whatever. But here we are rotating about this y-axis, so no problem. But in both cases, it's the same actually. There is no difference of the rotation axis. Okay. Okay. So now let's see how this composing transformations work. So let's say this is your x, y, z. So this is your like a original coordinate, and we are trying to get to x prime, y prime, z prime. So that's actually achieved by multiplying this with a matrix, right? And this is called the transformation matrix. Okay. So what you can do is basically there are like if you want to have multiple transformation, so basically you concatenate. So that means if you can have x prime, let's consider 2D. So x prime, y prime. So let's say this is m1, so this is m2, and so on, and then xy. But there are different ways to concatenate. So should m1 come before m2 or m2 come before m1? So there are basically two ways to concatenate. Okay. The first one is pre-multiplication. So in the pre-multiplication, what happens? So let's say this is your existing matrix. So this is your existing matrix, and basically, and you are trying to get a new matrix B. So this is your new matrix. So and you're trying to get into C. So C should be B multiplied by A. Okay. And for the case of post multiplication, so it's basically the opposite. So if you're trying to get to C, so then basically it should be A multiplied by B. Okay. Actually, OpenGL uses this post multiplication in its fixed pipeline. So whenever you consider this series of transformation, you can always assume that by default it's a post multiplication in case of OpenGL. So that means that the new matrix will be after the existing matrix. Okay. So this can be thought of these two type of things. So pre-multiplication and post-multiplication can be thought of as kind of from two point of view. So you can consider pre-multiplication as a kind of from a global coordinate point of view, and this one post-multiplication we can consider from a local coordinate point of view. Okay. So let's take an example and then see how this looks like, this global coordinate point of view and local coordinate point of view. And basically you will see that they are basically the same. I mean, there is no effect, but when you design your code, actually you have to keep this in mind and design accordingly. So if we see like a global coordinate point of view. Okay. So let's say we have a like a square or something. Okay. Okay, so let's consider a series of transformation. So let's consider rotate by 30 degree, then followed by translate by like 2 along x-axis and 0 along y-axis, and then scale by 0.5, 0.5. So that means we are decreasing the size. Okay. Okay. So this was your original shape. Okay. So after you rotate, what happens? So this becomes something like, it will look something like this because it's already rotated. And then you translate by amount 2. So what will happen? It will shift a bit further. It will come here and then scale by 5. So that means it will come a bit shorter, something like this. Okay. So now if you consider in a, like a local coordinate view, what will happen? So this was your original object here. So you rotate. Right? Okay. So by the way, in this case, okay, let me first do this and then we can try this. So here it was something like this, right? So now it will be rotated around its own, is exactly the same place. Okay. So now what happens when you rotate this? So that means your coordinate axis is basically again like a local coordinate is changing. So now you have to consider everything from a local coordinate point of view. So that means this is your x-axis now. So previously it was your x-axis. So you can consider this is as x prime. So then if you translate this, what will happen? So it will translate along here, not along here. So that means it will come somewhere here, right? And then eventually if you scale it, it will become basically like this. So they are basically the same. So you will get an end effect as the same, but you have to formulate your problem in such a way whether you are doing a global coordinate point of view, then basically you do your pre-multiplication or otherwise post-multiplication. So that means in this case, so if we try to consider, let's say v is like the vector or like x prime, y prime, like whatever is the point. So v prime will be the matrix multiplied with the original point, right? So in this case, so my series of transformation will be like a kind of pre-multiplying. So that means will be like scaling multiplied by then the translation and then the rotation and then basically the v. Then you get the effect like this here. But in this case, if you try to do in like a local coordinate point of view, then basically your v prime should be again m multiplied by v, but in this case it should be post multiplied. So that means we do rotation followed by translation followed by scaling of that one. Okay. So basically these are the same, but make sure that OpenGL uses this one, so it's much easier to handle sometimes with the objects being actually manipulated in its local coordinate frame. Okay. So if we try to do a simple experiment, sorry, it doesn't allow anything in between. Okay, let's try to write somewhere here. So let's say there is a coordinate system here. Let's say this is a C1 coordinate system, and let's say here is a C2 coordinate system. Okay, let's say this angle is 60 degree, and this coordinate is 5, 5. Okay, so if we try to transform from C1 to C2, so what should be the sequence? First translate by 5, 5, then rotate by 60 degree, or rotate by 60 and then translate by 5, 5. What should be the answer? This one or this one? Any idea?
The first one.
The first one? Okay, so what will happen if we do the yes, somebody was trying to say something.
The first one.
First one, yes, because if you try to rotate this, basically this becomes your like x coordinate and this becomes your y coordinate. So that means then if you try to transform, then basically it moves somewhere like here. So yes, right. So it should be the first one. So translation followed by rotation. So this is very important because like rotation and translation are basically order dependent. Translation is not order dependent. You can do multiple transformation without any problem, but rotation is problematic, and rotation in conjunction with translation is also problematic. So so that's why you have to remember that OpenGL uses this local coordinate system. Okay. Okay, so this was pretty much most of the things about OpenGL. I try to give you an overview of what OpenGL does in most of the functions. So in the labs, we will try to have some simple examples. I will also share some web pages where you can see some examples of OpenGL coding. You can also look at the web definitely. So try to get accustomed, because this will be very helpful for you, and to solve the assignments, and also to know things in a much better way. So in the lab, I will share you some like some links, and also with some small code snippets, and I will try to give you some small exercise to do testing with that type of thing. Okay, and then we'll see how things actually go. Okay, so
Sir, one
now,
question.
yes, yes.
Sir, how this for the GL vertex 2i, that kind of functions, so
Mhm.
how the screen is dividing itself means, means up to how much is the y values, or how much is the x values?
How much is the
Because
y value?
mostly 0 and 1 because I have seen, sir, mostly 0 and 1 is put, but means whether that values can be changed, or it is like, means the how is the device coordinate system that OpenGL is assuming,
So
what are
usually
the possible values?
so you can use vertex 2i or vertex 2f, so for floating point also. But usually in general case, it's usually from 0 to 1. So it depends again on your like a viewing window. How do you define? But in most of the cases, you will see between 0 to 1, because it's usually like a normalized. But you can use other values also. If you define, it depends again on your construction. Like how do you actually construct this from your viewport. I was showing you the viewport, right? Like which part of the screen is visible and all these things, and how do you open your window. So this one you can manipulate, of course. But yes, 0, 1, there should not be any problem with this.
Okay, sir. Maybe it will be cleared in the lab only, sir.
Yeah, maybe, yes. It's hard to like show example here. So maybe in the lab we can see some examples, and then see how actually it's looking like. Okay.
Okay, sir. Thank you, sir.
Okay. Okay, so this one was okay. In this example, actually, I was showing the same thing. So here, so this code basically draws the green arrow, and basically I was trying to show that rotation and translation are basically order dependent. So that's what I was explaining in the board. Okay, no worries. Okay, so let's. Okay, so now we move to the next topic of Bressenham's line drawing and circle drawing algorithms. So basically, actually, we now enter in the core graphics part, where actually you see the techniques, how actually they work. Okay. So here actually we'll see how to draw lines and circles in a very effective manner. But let me see where is the thing. Maybe I will use the board. Okay. Okay. Um, so Bressenham's algorithms. Okay. Uh, so initially we'll start with line drawing algorithm. So line drawing algorithm is a type of algorithm that determines the points in a n-dimensional raster display. Okay, so that means raster display means basically where you place your pixels. Okay, so that should be selected in order from a like a close approximation of a straight line between 2 points. I will show you what is meant by close approximation between of a straight line in the raster device. But many times we are using this raster. This term we are using in many cases. But also sometimes you will see like another term also, which is called vector, right? So basically this is vector graphics and this is raster graphics. So there are some differences between vector graphics and raster graphics. So in raster graphics, vector graphics actually, so vector data use like a kind of x and y coordinate to define the location of points. So basically x, y coordinate. So these basically come from the sequential comment or mathematical statement. So these can come from mathematical statement or like a sequential command. And then the example of like a vector graphics examples are like PDF, what you see in the PDF files, EPS also. If you use LaTeX, then you will see EPS files very common. It's very common. Also, SVG format is also from the vector graphics. And in the raster graphics, it's basically uses a matrix of square area to define where the features are located. So that means it's composed of pixels, directly the pixels, composed of pixels. Okay, and this format is very common. So all the format like JPG, like PMP, PIF, GIF, and all these things, they are all on a raster graphics. Okay, so that's why I mentioned that line drawing algorithm were basically determining like when you are trying to draw a line in a screen, basically. So this is composed of pixels, right? Like this. So when you are trying to draw a line, so you have to define which pixels to color actually, right? Because if this is my screen and I'm trying to draw this line, then I have to select the pixels which are to be turned on, which are to be colored for drawing the line. Okay. Okay. So what happens usually? What is the problem in the general case? So let's say this is your pixel grid. This is your screen or whatever. Okay. And like this is my pixel grid. Okay. So now I'm trying to draw a line between 2 points. Let's say from here to here. So what I will do, I just simply put a straight line like this. Okay. So now if I try to choose pixels, so that means in somewhere inside the drawing command, I have to turn the pixels on or color the pixels on. So if I try to color the pixels which are getting touched by the line, so how it will look like? So this pixel is okay, and here this is also, and this is also touching here. This is also touching here. This is also touching here and here. This one, this one, this one, this one. So you see, if I try to look at this without this, just imagine if you try to look at these painted pixels without this grid part, does it look like a line, very nice line? I mean, it looks like a kind of scattered. So I should not have unnecessarily colored this the pixel, actually this pixel, or 3 or 4 pixels here in the whole grid. So if I don't color all these pixels, then maybe it will look like a solid line, right? But with this type of naive approach, my line doesn't look like a line actually. So it will look something like a kind of this type of thing. It won't be a straight line, right? So what are my like desired qualities for straight line? So a desired qualities. So the line should have a continuous appearance, right? So it should have a continuous appearance. Because sometimes here this is not the best example, but sometimes you might see that some of the pixels are not painted because it's not touching that grid, so that's why it's looking like a kind of broken. So that's not desirable. So continuous appearance is one thing. Also uniform thickness. You see that thickness is not uniform. In this part of the line, actually, only one pixels are turned on. And in this part, actually, you see that it looks like much thicker. So this is not desirable. So we don't want this. So we want a much better line with a uniform thickness. Okay. Accuracy. So accuracy means the line should be looking like a line and not like a scattered thing like this. So this is not desirable. So accuracy is another important factor. And also the speed. I mean, if you try to develop an algorithm actually that draws a line in 1 hour, that's not good, right? Because you see the modern graphics applications where you are doing animation in movies and that's doing in real time. So if you try to spend a lot of time in line drawing, that's not a good thing. So all these four factors actually are important for developing a line on a raster screen actually, or raster device. So how it will look like in general. So basically, if this is a kind of my grid, and if I'm trying to draw a line like this, so this is my ideal line, right? But usually in the pixel grid, exactly getting the ideal line is not possible because we have a like a grid here, and whatever, no matter what you do, either you have to choose sometimes the best pixel combination that defines this line. So it might happen that actually, let's say if you're turning on this pixel here, and here it looks like this, here it looks like this. Whatever, okay. So that means, so these pixels that I'm turning on, they are basically the discrete approximation of the ideal line, right? So they are my discrete approximation of my ideal line. So that's why actually our goal will be to get a best line as like my discrete. If my discrete approximation is good, then we'll see it's very close to the ideal line. Although it might not be exactly the same as the ideal line, but at least as close as possible. So we try to minimize the distance between these two, in some sense. Okay. Okay. So if I try to draw a line, so let's try to see what is the problem with this type of approach. Okay, like a naive approach, and then we'll see what to do with this type of thing. Okay, let's take an example. Okay. So we try to draw a line. So draw a line between points x1, y1, and x2, y2. Okay. So what is the general line equation? Y is equal to mx plus b. Okay. So now for x1 and y1, we can write y1 is equal to mx1 plus b, and for this y2 is equal to mx2 plus b, right? So that means b is equal to y1 minus mx1, here b is equal to y2 minus mx2. We just equate them. And basically y1 minus mx1 is equal to y2 minus mx2. So that means y1 minus y2 is equal to m of x1 minus x2. So that means if we call this delta, delta of, let's say, delta y, let's call it delta x. So that means delta y is equal to m delta x. So this is my formula, right? If we try to draw a line between 2 points, so we can write this. Okay. So now consider a line. I will try to write here because otherwise it might be hard if I go to the next page. Okay. So now let's consider a line like this. Y is equal to 1/3 x plus 2/3. Okay. So what we'll try to do is that for every value of x, we try to see what is the value of y. Okay. So that means in this case, actually, what we'll try to do, we assume that there are x values, like a discrete x values, 1, 2, 3, 4, 5, and so on. So pixels are discrete, right? So that means we can assume that these are discrete values. And then from given x values, we try to see what are the y values, right? Y is also discrete, but we'll see if we are getting the correct discrete values or not. Okay, so that's why I have taken this example and then see like how it's actually looking like. So the idea is that you supply a series of x values and then go like a sequential. So that means if this is a straight line, what will happen? So for every discrete x value, there should be a y value. For here, there should be something. For here, there should be something. Here, there should be something. Here, there should be something. And we are trying to approximate this. Okay, nothing else. Okay, so to start with, let's start with the line at like a 1, 1. Okay. Okay. So let's make a table. Okay. So we have some x values, and here is some y value. Okay. Also, you will see that the y values are always not the integer. That means 1, 2, 3, 4. So we have to round it because you cannot plot a pixel. I mean, let's say this is your grid. So this is pixel 1, pixel 2, pixel 3. So if I tell you to paint pixel 1.5, is it possible that you paint here? No, this is not possible. Although these are very tiny, but you cannot go like floating point numbers here. So you have to uh, consider a single pixel, like exact pixel. So that means if it's 1.52, then basically maybe you round it to 2, or if it's a 1.47, you might round it to 1, or do something like this, right? So that's why we try to see what is the rounded value. Okay, round y. Okay. Okay, so let's take some values. So first, x is equal to 1. So what is y? So 1/3 plus 2/3. So that means 2 plus 1, 3. So y is equal to 1. So round y is equal to 1. Okay, no problem. Let's take x is equal to 2. So what is y? 2 plus 2. That means 4. That means it's 4/3. So what is the rounded y? Let's say it's 2. Okay. If I take x is equal to 3. So what is this? 3 plus 2, 5. That means 5 by 3. And this will be again 2. Okay. Let's make it bigger. Okay. So for 4, 4 plus 2, 2. And so this is 2. This is again 2. If I take 5, it will be 7 by 3. Okay. 2. If I take 6, 8 by 3. This will be 3. This is 7. This is 3. This is 3. Right? Okay. So probably you see the problem here, what's actually going on. Okay. So what here actually is computed is that, so that means you see that although x is actually increasing like this, so you see that multiple things are actually getting the same y value. That might happen if it's a kind of like straight line like this, but the problem is that what actually is computed here is that delta y is equal to m delta x. Okay, so that means the next y value, yi plus 1 minus yi, this is the delta, right? Means like yi plus 1, and this is yi. So this is my delta y. Okay. right, is equal to m of xi plus 1 minus xi. Okay, but this part xi plus 1 minus yi is equal to 1. Oh, sorry, I was showing it for x value. It's not x-axis, sorry, y-axis. Anyway, so xi plus 1 minus xi is equal to 1 because we considered the discrete like pixel values here like this. Okay, so that means if I put it 1 here, then yi plus 1 is equal to m plus yi, right? Now the problem is that if m is greater than 1, the traced line will not be solid. So why? Because delta y will be more compared to delta x. So that means the problematic case is here actually. So if my line is like this, so in this case delta y by delta x is equal to 1. This is absolutely fine. Okay, in this case delta y is less than delta x. This is absolutely fine. Why? Because if y is less than x, then you don't have any problem, and eventually you get the rounded value. And so that means why this is not a problem, because if the line is like this, so multiple x values are getting mapped to the same y value, and that's okay. But what happens in this case? So in this case delta y is greater than delta x. In this case, basically this is a problematic case, because we don't know at xi plus 1 which y to choose. So let's say this is my xi plus 1. So if there is a rounded value, because there will be large difference, so we don't know which one to choose. So let's say this is my computed y value. Okay, and here was yi, and here is yi plus 1. So which one to choose, I plus 1 or yi? If you go by the closer approximation, then sometimes it won't be like a solid line. It can be broken. So that means we have to find a way of which y to choose for each x value. Again, for the next x value, you will see that there is some y, but we don't know which pixel to choose, because pixels are like this type of grid. And let's say in your case, so sometimes you are getting a y here, sometimes you are getting a y here, y here. So that means these are somewhere in between the pixel grid. So you have to choose if you get a pixel here at the middle, are you choosing the next one or the previous one? So that's why this is a very problematic case. So Bressenham's algorithm actually what tries to do is to choose between yi and yi plus 1 for the only, okay, for this case actually we are talking about m is 0 to 1 in this case. So there are other cases as well, but we discuss only this one. Other cases are basically kind of symmetric, and you just interchange the value, and there is not much of a problem here. So basically the main fundamental thing about Bressenham's algo is basically at x I plus 1, we need to choose between yi and yi plus 1. So here, with the assumption that m is between 0 to 1, because we are considering this type of case only. There are other cases as well, okay? And also delta is equal to 1, because we are considering this discrete pixel grid, right? If delta is equal to 2, that's different, 3 is different. So that's why actually how this works. Okay. Okay. So let's actually start from here. Okay, so is it clear? Any question from here? If you're confused of what I'm trying to say, hmm? Let me know. So we are trying to choose the discrete pixels. Okay. All right. Okay. Okay. So that means let 0 m and delta is equal to 1. So this is a very useful assumption. Otherwise, it's invalid. Okay. Okay. Let's try to see how actually things look like here. So basically, this is my grid, and let's say sorry, coordinate system, and let's say this is the line I'm trying to draw. Okay. So let's say this is xi, and this is xi plus 1. Okay. So we get a y corresponding to xi plus 1, which is somewhere here. Okay. So let's say this is y. Okay. So this was your previous y. So that means in the pixel grid, and this is your next pixel. Okay. So that means at here xi plus 1, we have got a value y, and where we are getting this value like this. Like this is basically the values we are getting actually. X is incrementing like sequentially, as like a 1, 2, 3, 4 as a discrete intervals. Okay, and we are getting some y values, and we don't know which y to choose in this case, because this is my valid pixel yi and yi plus 1, and each y we have to decide whether to choose yi or yi plus 1. Okay, let's call this distance y to yi as d1, and let's call this as d2. Okay. Well, okay. So let's see how this thing will look like. So that means y is equal to m x I plus 1 plus b on the same equation, and we are doing it for this point x I plus 1th point. Okay. So what will be my d1? d1 is this distance, that means y minus yi. Okay. So that means mx I plus 1 plus b minus yi. Okay. And what will be my d2? yi plus 1 minus yi plus 1 minus y is y m x I plus 1 minus b. Okay, but this yi plus 1. Okay, so we are considering discrete pixels, right? So what is the distance between y? Can anybody tell what is the distance between yi and yi plus 1? So we are considering discrete pixels here. So what should be the value? Yi plus
1.
1, exactly. So yi plus 1 is actually yi plus 1 is equal to yi plus 1, right? Okay. So that means we can write d2 is equal to yi plus 1 minus mx I plus 1 minus b. Okay. So this is my d1, and this is my d2. Okay. So now let's try to subtract between these two, d1 and d2, and then try to see which one is closer. Either d1 is closer or d2 is closer, how actually things look like. Okay. So if we try to do d1 minus d2 is equal to, okay, this is problematic because I have to every time go from here to here. Anyway, but let's see. Xi plus 1. Okay. M xi plus 1 plus b minus, okay, yi. Sorry. Yes, minus yi. Okay. Minus d2 means, oh, sorry. yi plus 1 minus mx r plus 1 minus b. Okay, so just simplify this equation. So x xi plus 1 and mxi plus 1, there is a negative sign, so that means 2m xi plus 1. Okay, so there is yi and here is 1 yi, so that means 2 yi. Okay, thus here is b, here is another b with a positive sign, so that means plus 2b and that's minus 1. Okay, okay, so in this case again with the same logic, what will be xi plus 1 is equal to what kind of rate? Can you repeat again what you were saying in the previous answer?
xi plus 1.
Yes, xi plus 1. So we just simply put here m xi plus 1 minus 2yi plus 2b minus 1. So we just replace m by delta. Okay, so what is m? M is equal to delta y by delta x, right? So basically we write 2 delta y by delta x xi plus 1, okay, minus 2yi plus 2b minus 1. So that means delta x of d1 minus d2 is equal to 2 delta y xi. I'm just putting things in a straight manner, okay? Plus 2 delta y minus 2, again delta x is multiplied, so 2 delta x yi plus 2b delta x minus delta x. Okay, that means we have it here with the formula for delta x of this. Okay? So we might need this later. Okay. Okay. So now what we try to do is that we try to associate these with some quantity. Let's call it pi. So pi is equal to delta x of d1 minus d2. Okay. So basically, we will try to see what happens if pi is less than 0. If pi less than 0, then we choose yi. Why? Because of this delta is less than 0 means this one is closer, d1 is basically closer, and if this one is sorry, if the pi is less than 0, so that means yi is closer, or otherwise yi plus 1 is closer. So that's what we are trying to do here. So if pi is less than 0, then we choose yi, or otherwise we choose yi plus 1. So now the point is, I mean, how can we find the equation of P1? Or like we have to start somewhere. So we have to find the equation of like a P1 or also Pi in terms of like a delta x, delta y, and also Pi plus 1 in terms of Pi, right? So that means we have to find the equation of P1, and also we have to find the equation of Pi plus 1 in terms of like a Pi. So these things we have to do, right? So we have to do a little bit algebra here to get these values. So I think today we can stop here, and tomorrow we can see how actually we can progress and get these values, and then we'll see actually how the algorithm actually looks like. Okay, and Bresenham is very interesting. You will see. Actually, your first assignment will be on Bresenham's algorithm, so it will be very nice if you understand things nicely. Okay. So today we stop here because it's 10, and we finish this tomorrow, and then we do the labs. Okay. So if you have any question, please ask, or otherwise we can stop here. Okay. No question? Okay, so thank you for attending the class. So we stop here. Thank you.
Thank you, sir.